All right, so up to this point, we talked about the chromatic number, which focused on the coloring of the vertices. And the adjacent ones, the adjacent vertices had to have different colors. Now we're going to ask ourselves a new question here. We're going to here color the edges. All right, so no two edges sharing a vertex have the same color. All right, so when we were talking about the chromatic number, all right, so G, we said that two vertices were adjacent if they were connected to an edge. So if we call this vertex 1, vertex 2, they were adjacent if they were connected to by an edge. Now, when dealing with edge coloring, right, adjacent vertices are if they here, so if we have these E1, E2, E3, if they are all kind of meeting at this vertex 1, then we say E1 through E3, those are all adjacent edges here. Okay, so they share an endpoint, right? Whether it's on this side or the other end of each of those edges, all right? So here, E1 through E3, they're adjacent, and then here, I guess, 2, 3. All right, so E1 and E2 are adjacent at 2, and at 1, E1 through E3 are adjacent. Okay, so what we're going to focus on here, talk about what's we're going to define as the chromatic index. Right, which we are going to label as chi prime of G. Right, and this is going to be the minimum number of colors needed for a proper edge coloring. Okay, and by proper edge, it means no adjacent edges have the same color. All right, now since each edge that meets at a vertex would have to have the same color, that means that we have a very solid lower bound for the chromatic index. And that lower bound is going to be the highest degree. So the chromatic index of a graph G will always be greater than or equal to the maximum degree of a vertex in graph G. All right, since if the maximum, if we're at the maximum vertex, all of those edges need to be a different coloring for it to be a proper edge coloring. Okay. All right. So let's take a look at an example from our textbook here in the Levin book. This is example 2.5.6. All right, now 6 friends. So the example is talking about 6 friends. All right, each play each other once. All right, so they're playing chess. All right, and here each game is an hour. All right, and they each want to play each other once. Okay. All right. So yeah, that's roughly about what does that turn out to be like? About 15 games, it seems. Now, here we do have to just what we want to see is, well, you know, if each game takes an hour, right? what's the best way I can maximize that time, right? Because if there's 15 games, right, we don't have 15 hours, right? Maybe it can be done less, right? So we can think of this as a complete graph, right? K6, where the vertices are the friends, right? And the edges are the games. Are the games. Okay? And we want to determine how we can have a proper coloring here, right? Now, here, if we see, so what we have here is the complete graph K6, right? We can think of the vertices representing the friends, right? And we know that there's a lower bound here of 5, right? Well, as it turns out, right, if we do have 5, it looks like we can have 5 be the proper coloring here. All right, so it's at minimum 5, and I don't think we actually need to do anything besides that, right? Because here, if we have 1, 2, 3, 4, 5, right, and if we kind of work our way here, right, this is 2, then we can have the other 4 colors here, and then vice versa here, right, where we just have to make sure that we don't overlap any of the colors at the adjacent edges, right? But in this particular one, the minimum coloring is going to be 5, right? So here, right? So as it turns out, our K6 is going to be 5. So what that means in terms of the problem is that the friends will need 5 hours to complete their play. All right, so they will be able to set it up so that at each hour they can rotate, and at the end of those 5 hours, right, then everyone would have played everybody else. Right now, interesting note here is that if we happen to delete a vertex, right? Oops. Let's see, undo. If we happen to delete a vertex, then it would also still be 5, right? We would still need the 5 hours here, right? So that's an interesting note here. That happens here just because of the nature of the graphs here, where we remove one player and we're left with an odd number of players, right? So that means that at any time, right, someone would have to be sitting a game out. All right. Okay. Now, as it turns out here, so a theorem from our book, there is actually a very straightforward theorem where it says for any graph G, prime G, the chromatic index is either delta G or delta G plus 1. Okay. All right, so that is pretty straightforward. The real problem is identifying which one is it, right? So here, so we classified these two types of situations we call a class 1 graph, where chi prime of G is going to be equal to delta G, and then a class 2 graph when chi prime G is delta G plus 1. All right, and going further, our bipartite graphs are always class 1. So that would be for sure. If it's bipartite, then it is class 1, right? Or whatever the maximum degree happens to be. Okay. Now deciding where each graph belongs, whether it's class 1 or class 2, it's not always easy, right? So you really just have to go by just kind of almost trial and error, and which can be, or developing an algorithm to check, right? Like a computer algorithm, like some kind of program that will check the adjacency of the edges, right, and determining what the proper edge coloring would be. All right. Okay. Now another thing that comes up is when trying to model situations, should you be looking for the chromatic number or the chromatic index, right? A proper vertex coloring or a proper edge coloring, right? So a rule of thumb here is when to use a vertex coloring or the chromatic, excuse me, the chromatic number, right? A proper vertex coloring, okay, G. When we think of objects that conflict, or they cannot share a resource, right? Such as classes and time slots, right? Or if you had different chemicals that you want to store in certain cabinets, right? Then we want to make sure that chemicals that shouldn't be next to each other aren't in the same cabinet, right? Etc. Right? And edge coloring. We want to use pairings that happen simultaneously and cannot overlap, right? So like the game example that I just covered right now, right? So we have games going on at the same time, but we can have different. We can overlap where a person is playing more than one game, right? So yeah. So games in a tournament. Okay. All right. And edge coloring we called chi prime of G.